Welcome to my talk. Today, I'm going to talk about a very exciting topic. That is, what is the physical basis of E equals mc squared? I'm sure all of you have heard about this equation before. In fact, E equals mc squared is probably the most famous formula in science today. Now, according to most of the textbooks, E equals mc squared was proposed by Einstein based on special relativity. But is this really true? So let's look at the publication record. Let's look at the literature. Let's examine if this is really true.
The formula E equals mc squared is often thought to be due to relativity. But is this conventional thinking really correct? What is the reason that makes us to question this conventional thinking? Well, there are at least three reasons. First, the concept of mass-energy equivalence had been suggested before relativity. And second, Einstein's argument on E equals mc squared were based on thought experiments instead of first principles. And third, these thought experiments were not directly related to the principle of relativity. Instead, they were mostly based on the argument that radiation and matter behave similarly. Now let's look at some of the early publications relate to the development of the concept of energy mass equivalent. Now you probably remember, okay, special relativity was proposed by Einstein in a paper, it's published in 1905, okay, this paper. But before 1905, there have been many publications suggest the concept that mass and energy could be converted between each other. In fact, the relation of E equals mc squared was suggested by Poincare in 1900. Einstein, after published his special relativity paper in 1905, in the same year, he also published a very short paper suggesting that mass and energy could be related. Now, this paper is very short. In fact, you can find it in most of the reference book on relativity. English translation of the title of this paper is "Does the inertia of a body depend upon its energy content?" And this paper is only a little bit more than 2 pages long. It's a very, very short paper, a very simple argument. So that was the first paper published by Einstein on E mc squared. This paper, however, has a number of difficulties. First, it's not based on a general situation, it's based on a special situation. Einstein called it thought experiment. And the result, E equals mc squared, was not an exact mathematical result. It was an approximation under the condition that the traveling speed of the system is much less than the speed of light. And this thought experiment was unrealistic. In reality, we cannot conduct that experiment proposed by Einstein. And finally, that this paper involves some steps that is not consistent with special relativity. So Einstein was not satisfied with this paper. So in the next year, 1906, he published another paper based on the argument of conservation of center of gravity. And that paper also has some problem. And so in the following, say 30 years, Einstein wrote many more papers. In 1907, he published 2 papers, 1908, 1909, 1911, 12, and all the way up to 1946. Einstein has published about a dozen papers trying to prove E equals mc squared. Now recently, there were several detailed literature review on Einstein's work on this topic of E mc squared. Here's what they found. Okay, review written by Tony Rothman, published in Scientific American in 2015, and here's the conclusion of Rothman's literature review. He said Einstein was aware of the shortcoming of his derivation in 1905-1906 and wrote a half dozen more papers over the next 40 years, trying to patch things up, but arguably never succeeded. So according to this review, Einstein never really gave a satisfactory derivation of E mc squared. Another review, actually, Eugene Hack published several papers in the last 10 years in American Journal of Physics. And here's the conclusion of his review. Now, this is directly quoted from his 2011 paper in American Journal of Physics. He found that Einstein produced about 18 derivations and demonstrate aiming to establish the mass-energy conversion principles. Now, in the review point of view, or the review concluded that although each of these papers give evidence for the applicability of E mc squared to a particular set of circumstances, but no one derivation or collection of them taken together succeed in providing a definitive proof of its complete generality. So based on this literature review, well, we may conclude that E mc squared is actually not derived from relativity. It was derived from the fourth experiment of Einstein, which was based on the concept that matter and radiation behave similarly. Now, if that is the case, then how can we explain the physical basics of E mc squared? Now, based on Einstein's approach, the thinking radiation and matter behave similarly, so that inspired us to think that could be due to quantum mechanics. Why? Because quantum mechanics, that the wave and matter are very similar. So our new hypothesis is that this E mc squared relation is really due to quantum mechanics. It's the result of quantum mechanics. And also, it is because the matter is composed of wave. Now, let's examine this, if it makes sense or not. Well, the first thing we need to remember is that in quantum mechanics, the quantum particle is more like a wave packet than a point mass. And how do we know that? How do we know that in the quantum world, the particle behaves like a wave? Well, let's look at some of the experimental results. We know in the last 70 years, there has been many so-called particle collider building. They accelerate particle to very high speed, let them collide, and then look at the bits come out from these collisions. So what they found is the following. First, they found a particle can be created from nowhere. You collide, say, maybe two electrons together, and suddenly you are getting other particle, like maybe a tau particle, maybe a different kind, a kaon, and so on. And furthermore, some particle can be converted into different type of particle during their decay process. So that implies the particle cannot be a mechanical object. If a mechanical object, it cannot suddenly appear in the vacuum. And also a mechanical object cannot be converted into a different mechanical object suddenly. Okay? So the only explanation is that the quantum particle is an excitation wave. Now, in fact, this idea has been proposed more than 100 years ago, because we know in the end of the 19th century, why people start to think about quantum mechanics is because Max Planck's work on this so-called black-body radiation, and he found that the emission of light is in package. We call it in package of, this package energy is called a photon. So in Planck's relation already show that the particle property energy is related to the frequency of the wave. And about 20 years after Planck's relation, de Broglie also proposed a relation now called the de Broglie's relation, that the momentum of this particle is related to the wave vector of the wave packet. And so that 100 years ago, that the physicists already found out that the matter actually, we know matter is made up of atom make up subatomic particle. And this subatomic particle actually has two properties. One is a particle property, and second, a wave property. And this is called the wave-particle duality. And the physical basics of wave-particle duality is a very important subject in the study of quantum mechanics today. Now, someone may say, well, it's easy to understand a mechanical object has mass, but how can a wave packet also has mass? Well, it's not difficult to see that, because we know that the mass is defined actually by momentum. We know a momentum equal to mass times the velocity of the object. Now, if something has momentum and it has velocity, then you can find the mass. Well, in fact, if you look at in the classical world, say the object is like a point mass, then of course it has a velocity, it has a momentum, and it has a mass. But in the quantum world, that this particle is more like a wave. Now the wave also has a momentum. That's based on the de Broglie relation. And the wave also has a speed that is called the group velocity of the wave packet. Now if you have a momentum, if you have a speed, then momentum divided by the speed is equal to the mass or effective mass. Now let's look at some example. Let's look at the particle of light that is called photon. We know photon is a wave packet. In fact, we know it's an electromagnetic wave. And it can be demonstrated very easily that this wave obeyed the relationship of a mass-energy equivalence. Or we can say the mass of this photon can be demonstrated is related to energy. Now, how do we see that? It's really simple. Three-line argument, okay? It does not take a lot of mathematics. Well, first we know mass is defined from the momentum, as I told you earlier. The momentum equal to mass times the speed. For the photon, the speed is the speed of light, c. So photon, p equal to mc. Now from the de Broglie relation, we know p equal to h bar times k. H bar is the Planck's constant, k is the wave vector. The wave vector is equal to the what? Equal to 2 pi over lambda, and is equal to the frequency divided by the speed. Now, we know, so therefore the effective mass is the momentum divided by the velocity, which is a c, so it's equal to h nu over c squared. But then, from the Planck's constant, we know h nu equal to E. E is the energy of photon. So now m is equal to E over c squared, or E is equal to mc squared. So here, we can see it just very simply that E equal mc squared holds for photon, and Y equal mc squared is because of the de Broglie relation and the Planck's relation. And these two relations are the basic law of quantum mechanics. Okay, so this, at least in the case of photon, it's very easy to demonstrate that the E equal mc squared is a result of the quantum relation. Now, someone may say, well, the photon is a special particle, but it has no rest mass. So when you show the mass is the effective mass. What about the particle that have rest mass, such as electrons, such as the proton, neutron, and so on? Now, it turns out not only photon behave like a wave, the massive particle also behave like a wave. Now, how do we know that? There were a silly experiment about 100 years ago and called the Deflection Experiment. They're using a beam particle to bombard a crystal surface and look at the deflected signal. And what they found is that they obey a law called the Black's diffraction law. And this Black diffraction is because of the wave properties of the object. Is 100 years ago, people found out that not only photons obey this wave property, electrons, neutrons, and the helium particles, they all behave like wave in this diffraction experiment. In fact, this was so important, this result so important, in the 1930s, two scientists, two physicists got the Nobel Prize in Physics based on this finding in the diffraction experiment. So now it's very clear that all quantum particles are excitation wave. The excitation wave of what? Well, since the particle travel in the so-called space, we call it vacuum. So this particle must be excitation wave of this medium called vacuum. Now, someone may say, wait a minute. Vacuum usually means nothing or empty space between any object. How could the vacuum would generate any wave? Well, I would like to remind our audience, assuming the vacuum is the empty space is a very old model. It's the classical model, like the Newtonian model. Newtonian mechanics. In today's in the modern physics, we have plenty of evidence showing that the vacuum is not an empty space. It has some very rich physical property. In fact, if you look at cosmology today, one of the most important theory in cosmology is Big Bang. That's what they think how our universe begins. And the beginning of our universe is due to Big Bang. What is Big Bang? Big Bang is a quantum fluctuation of the vacuum. So you can see this quantum fluctuation could be very powerful. So based on this new understanding, so we can make the following hypothesis, that the particles are excitation wave of the vacuum medium. And different excitation mode represent different type of particles. Now, once we understand or agree with this hypothesis, then it's very easy to find out what is the properties of the particle is during their motion. Okay, so the idea is trying to find the quantum wave function of a particle during its movement. Now, this can be done very simply. First, we can solve the wave equation of the vacuum. And this wave equation, of course, is based on the known property of the vacuum. And this wave equation has multiple solutions. And they're supposed to represent different type of excitation mode. Now, according to our hypothesis, each solution represents a different type of particle. Now let's look at some example. The first solution, or the simplest solution for the wave equation of the vacuum is like this. This is just a plane wave. In this plane wave, it has two wave parameters, k and omega. It's just like before. K is the wave vector, omega is the frequency. Now, in this solution, one can show omega equal to ck. C is the speed of light. Now, you may recognize that this dispersion relation is the same as the dispersion of light, from the classical electrodynamics. Now, based on this result, we may conclude that the plane wave solution represents the wave function of a photon, because its dispersion relation is the same as the dispersion relation of light. Now, what about the other solution? The more complex solution for the wave equation of vacuum is look like this, okay? This look complicated, and the Jm here is the best function of the first type. And well, the important, you don't need to worry about the equation. The only thing you need to focus is its dispersion relation. It's the dispersion relation of this vertex light wave is omega squared equals c squared, k squared, and l squared. Omega is frequency, k is the wave vector, and L is the transverse wave vector. Later we will explain what it is, okay? Well, actually, you can see this is a solution. So this is the transverse plane. So the particle is moving up to down, up and down. And this is the transverse plane. And you can see this oscillation. And this oscillation has a certain wavelength, and this wavelength is related to L. And this solution appears to represent a massive particle. Now, how do we know that? That is because this dispersion relation will agree with the energy momentum relation of a massive particle. Now let's look at how could that be. Well, again, let's look at the Planck's relation and the de Broglie relation. So E equal h omega and P equal to h bar k. Now, the dispersion relation of this vertex light solution is this. I just showed you. And that you can probably, since omega square is actually related to E square, the k square is related to P square, and the L square is related to the mass square. Okay, so you can see that this dispersion relation of this vertex wave agree with the so-called energy momentum relation of a massive particle. So that's is why we think this is the solution representing the massive particle. Now, from this energy momentum relation, it's very easy to derive the E and the square. Okay. Now, the mathematics is very simple. Well, here we don't want to bother you with detail, but if you want to look at the derivation, you can go back to check my paper. At the end of this talk, I'm going to give you the reference. Okay. So E times the square can be derived very simply from this energy momentum relation. So that means the relation mass energy equivalent is due to wave nature of the particle. So we give you actually two examples. One is the example of the photon, which is straightforward. The second example is the particle with less mass. Now that's, the calculus is more complicated. What I give you is the essential steps, so it can be demonstrated. So E and the square can be derived based on this quantum relation. Now, this wave model or wave hypothesis actually has a very interesting philosophical implication. What it proposed is that there is a definite relation or one-to-one relation between matter and wave. If you look at the object making up matter, so like a massive particle, they have a certain physical property, such as energy, momentum, mass, velocity, and so on. Now, what we found is in the quantum world that all or each of these particle physical property is related to a wave property. For example, the energy of the particle is related to the frequency of the wave packet. The momentum particle is related to the wave vector of the wave packet. the mass of the particle is related to the transverse wave vector of the wave packet. And based on this, and also based on the so-called energy momentum relation, is no more than a dispersion relation of this matter wave. Okay? So it's very easy. So now the world will appear to be very harmonious. Another thing we may notice is that all of these physical property of the particle, they are related to 1 over the periods in the wave field. For example, omega is equal to 1 over t, k is 1 over lambda L, and L is 1 over the lambda t. So what is 1 over period? Actually, 1 over period meaning the curvature of a bending something. Say, suppose you look at this, this is a medium. If the wave is traveling in this medium, so when the wave comes, it will bend it. So it will bend it. You can see this is. So what is the period? A period actually is a period meaning how fast that this medium being bent. Okay? If you look at, say, this is 1/2 a period, okay? If this period is very small, that means the curvature is very high. If the period is very long, that means the curvature is very small. So 1 over period actually means how large is the curvature when you bend the medium, when the wave passes through. Okay? Now this makes sense. Why it makes sense? So if energy, momentum, and mass proportional 1 over the period, that means they're proportional to the curvature of bending vacuum medium. And we know when a wave passes through, how sharp you bend this medium depends on how much work you do on it. So in order to have a high curvature of bending medium, you need to put more work into that. And so what this means is that no matter energy, momentum, or mass, they are all related to how much work we put on in bending the medium. Okay? So this now is very interesting. So that means, from based on our previous analysis, not only we know the quantum particle is an excitation wave of the vacuum medium, we also found energy, momentum, and mass can all be treated on the same footing. What footing? They are all related to the curvature of a bending the vacuum medium. Okay? So but they are measuring this period or measuring this curvature in different dimensions. Either measured in the time dimension, or you're measuring in the spatial dimension, or you're measuring in the different direction of the spatial direction. Okay, so that means energy, momentum, mass actually has a very similar physical meaning. So that explains why the energy and mass are equivalent. And that explains why E can be equivalent to mass. Why E equals mc squared. Okay, that's very nice. Now, this wave hypothesis not only give us an understanding about the physical basics of E equals mc squared, it also can answer another important question. What is this question? That is why no particle can travel faster than the speed of light. Now, this is a very peculiar thing. If you regard the vacuum as an empty space and the particle is just a mechanical object, you should be able to accelerate this object at any speed you want to. There should be no speed limit. The more energy you put in, they can go faster. But in reality, we know that's not the case. So how to explain that? Now, in Einstein's day, so he explained it by just treating that observation as a postulate. They say, well, that's how nature is. Okay, so he just declared, we don't know why, but that's the way it works. Okay, and so this is a postulate that nothing can travel faster than the speed of light. But using the wave model, it's very easy to see the physical basics of that. Why? Because now we know the particle is just an oscillation wave, excitation wave of the vacuum medium. And we know any excitation wave, when the wave moves on the medium, it has a fixed limit of speed. And the speed of this wave transmission depends on the physical property of the wave medium. Okay? So it is natural that any excitation wave, when they move in this wave medium, they should have a limiting speed. It's just like a sound traveling in the air, there's a speed of sound. When the other wave, traveling in some sort of a solid, there is also a speed limit for it. Okay? So it's well known that a wave should have a limiting speed, and that traveling speed of the wave depends on the physical property of the wave medium. So now if particle is an excitation wave of the vacuum, so the speed of the particle will be determined by the wave property of the vacuum medium. In fact, one can show mathematically that these wave hypotheses predict that a photon should always travel at a constant speed, c. And the speed of a massive particle is less than c. Okay, this can be demonstrated, can be mathematically. Okay, for those people that are interested, get checked my paper. All right. So that's really nice. Now, finally, that people may ask and say, well, your theoretical hypothesis could be interesting because it explains two things. It explains what is the physical basics of E equals mc squared, and also it explains that why a particle cannot travel faster than the speed of light in the vacuum. But does it have any experimental evidence? Can it be tested by an experiment? Now, as we know, any viable hypothesis in science must be testable in experiment. So can our model, our wave model, be tested by experiment? The answer is yes, we can test it. In fact, just a few years ago, I already published a paper to propose an experiment to test this wave hypothesis. So this experiment is really to test one key question. Is there a resting frame in our universe? Now, why this question is important? According to the classical view, the vacuum is an empty space, okay? And so Einstein assumed that any inertial frame should be equivalent. So this is like a symmetry, okay? But in the wave hypothesis, the vacuum is a wave medium. It is not empty space. So the vacuum medium itself will provide a reference frame, and we may call it the resting frame. Okay? So now if a particle, so moving in this wave medium, then you can measure the speed of the particle against the stationary frame of this wave medium. Now, we may recall, or you may know, that the moving mass of a particle actually depends on its speed against reference frame. So that means that if we can have a very precise measurement of the moving mass of the particle in different directions moving in our universe, then if there is no resting frame, then you will see in all directions it's moved the same. But if there is a resting frame, so some of the direction you will see the particle will move faster and other directions move slower. And the reason is because this experiment is done on Earth, and the Earth is moving at a certain speed against this vacuum medium. Okay, so some of the direction that the movement of the particle is parallel to the movement of the Earth, and in some other situation it may be against, maybe in a different direction against the moving Earth, and then the speed will become shorter. So this is the basic principle, okay? And this experiment actually is doable. So using our current technology, it's possible to detect the difference, the variation of this moving mass in different direction. And so this paper was published in the European Physical Journal. And this paper actually received quite a lot of attention, okay? And because it deals with a very fundamental question, okay? So when my paper was published, it was reported in quite a number of scientific news media. For example, you can see in the Europhysics News, they reported, and also in the website of the AAAS, the publisher of the science magazine, they also report that, okay? For those people that are interested in this experiment, you can just read my paper. In fact, here are the reference, okay? The first paper is about our discussion today, that what is the physical basics of a mass energy equivalent. And the second paper is the post-experimental test. Okay. Okay, well, thank you.
So, from this talk, I hope you will get a take-home message that yes, in the quantum world, matter is composed of particles. But this particle does not look exactly like a point mass. Instead, it's more like a wave packet. And it's because of the wave properties of the particle that explain why energy and mass can be converted. So in other words, E equals mc squared is not the consequence of classical physics, but it is a result of quantum mechanics. So E equals mc squared is really due to quantum mechanics. Okay, bye-bye.